All right. So let's continue on DES and let's check some of the examples and numericals on that as well today. But before going to that, as I'm doing for the last few classes, let us quickly recap on some of the things that we have discussed on last day itself. Let the but anyway, where we stand at this point is that we know that what will be the block diagram and the structure of DES. And we have observed that there are 16 such rounds which are called as Fiestel rounds. And each of the Fiestel round will have certain amount of function. And in that function, the primary objective of that function is to convert the 64-bit data into two halves of 32-bit each. And finally, that 32-bit data is converted to internally to some kind of a 48-bit once again, just like in over here. And a portion of the data I'm talking about, the right hand side to be precise. Along with that, we have some expansion option in which we are expanding the 32-bit to 48-bit by certain operations, which I think I told you on last this class. And this is the diagram of it to wrap it off. So you can observe the principle was that the last bit of the previous block will be the first bit to the next block. So that was the principle. And there will be the cyclic rotation at both the ends of the blocks. The first and the last block will have a cyclic rotation of the bits. So that's what was discussed. And on that note, we had also found out that we have the key generation. All right, the key generation, I think I have S-box also we had discussed on last day. Look, wait. He also eager for okay. That's the intruder. Anyway, and if you're given this S box, if you remember, we had also discussed that we had 8 S boxes for DES. And the one example that I'm showing you right now is one of the sample template for the S box. You can see S box 1, I think, and S box 8. So like that, there are other S box 2, 3, 4 like that. It will be there. So these are some of the template or the standard table, permutation table for the S boxes which are being used. If you remember, I told you that there will be 6 input and 4 output for it. So following this table, we are going to generate the output as with the process that we all know. The final bit and the last bit will be the row and the middle bits will be considered as the column. And if you observe the same thing I told you on last this class as well, that for S boxes, the row and the columns are in decimal numbers. So you have to convert that from binary to decimal and then change it back to binary once again. So that's all I discussed on last day itself. Now, this also is pretty okay. This is fine. So this is one of the example of such an process. If you observe that what will be if the input of the S box 1 is given by 10011, then what will be the output? All right. So this already I think we are all familiar with, and I don't think we need much time in understanding that why it is. But again, for people who are not there on Saturday's class, basically we are trying to find out using the same process as for the S box. We are trying to get hold of the binary data. We are converting back to the decimal value. You can observe that the result is 12. You can see here 12. You are getting actually the initial value is 11. We are converting that to decimal value of 3, and following the table we are trying to find out. Is there any doubt in that? Should I repeat this once again? So in this case the values are 1 1. So basically this is my row, and the in between elements will be 0 0 1. So 0 1 is in decimal value is 1. So basically we are intersecting at some point over here. So this table, if provided to you, you should be able to find out what is the exact decimal value. Now, based on the 12 decimal, you have to convert back to the binary data. So for the given inputs 10011, the output should be 1100. Right? So this was the process involved. Now this will change based on the table. That table only I have shown you over here, that this is the S1 box table. And the last one is S8 box table. Such that S2, S3, S4, all these tables will have elements. Also, I think we were in that process of discussing on how the key was generated. So let me just show you that over here. This I can skip. Yeah. So this is, I think, no, not, yeah, this one only. So in this case, we were generating the permutation PC1. If you remember, for both the slots, I did that. So if you remember, I told you the key will be initially of 64-bit. All right. How we are changing it to 56-bit? Last bit will be discarded. That last bit means it will be divided into 8 such blocks. For 8, 16, 24, 32 and all other 8 elements, those bits will be first reduced. So first of all, what will happen, that those 64-bit will be converted to 56-bit. After it is done with the 56-bit, then we have to use a process of dividing that into 2 halves of C0 and D0. If I'm not wrong, I think this is where we had ended our discussion. So let me just start off from that. So this is where I was talking about. So suppose I have a key. This key is 64-bit. Is it? Oops. What happened? Alright, so we have the key which is of 64-bit, and based on the process that you mentioned, we are changing it to, so we are going to something called as PC1, or we are calling that as a permutate choice 1, in which the 8th bit is discarded. So now we are getting something in terms of 56-bit, and as per our rule, we are dividing that also into 2 halves, which we are calling as C0 and D0. Alright, so both of these bit will be of 28-bit each. 28-bit duration. Alright. So this is where we actually stand right now. Now after that, what also I told, I think it happened with the second batch, not with the F1 slot, is that from this 56-bit, we have to convert back this to 48 bits. Because if you remember the slides that we had discussed, and if I go back to some of the previous slide, suppose over here, you can check the keys of 48 bits. The keys of 48 bits. So basically whatever happens, 56 needs to be converted back to 48 bits. So that I'm trying to explain to you. And for that, I told already, but still just for a reminder once again, I think I have missed for the F1, is that there is a certain rule for that as well, that how and why we are doing it. So the rule is, for first, second, 9th and 16th round, please make a note, left shift by 1 bit. So a single bit shift will happen for the rounds 1, 2, 9 and 16, and for the rest of the rounds, like for example 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14 and 15, there will be left shift of 2 bit each. So this is the rule, please make a note of it. This is after we have developed a 56-bit, we have to convert back that to a 48-bit. Okay, so for that, what we are trying to do, we are trying to make sure that there is a round shift that is happening with respect to this C0 and element. Alright, so this is an element, this is what we call as the process involving a shifting just to make the randomized element. So the 48-bit remains, the 56-bit still remains as it is, because it will still undergo another process of permutation. Alright, that will be called as PC2. So the PC1 is over here, we got a 56-bit. After this, actually, there will be this randomizer. This randomizer is based on the rule that I mentioned. So C0 and D0, suppose this is what the first round we are talking about. So the C0 bit, if it is in the first round, the key is generated, then one left shift will happen for both C and D. Okay, and if it is 2 or the third round, suppose second or third round that you are in, then there will be 2-bit shift that will take place. Okay, so let's just give you an example, then I'll come back, because after this R, there will be another block which will be called as PC2 also. And finally, we will receive the 48 bits over here. Okay, but before going to PC2 or the 48 bit, let's see about that value and how this randomizing is working. So let me do that. So what I am saying is, for example, instead of taking 64 bit, let's take a small example in which 0011, 0101. These are the 8 bit. We are just getting the same result. I'm trying to explain you the process. So suppose this is my 8 bit data, where this is my C0 and this is my D0. Alright, this is just an example I'm talking about. Now this goes through the randomizer part. So what will happen if it is in the first round, then there will be one left shift that will happen for both C0 and D0. That means it will be looking at 0110 and this will be 1010. That means this is being left shifted over here. Got it? So this will be my randomized key, still 8 bit data. After the C0 and the D0, the left and the right shift has been split it. If this is the first round I'm talking about. But suppose the same thing, suppose it is happening like we have a data 1100. This is in round 4 I'm talking about. Suppose round 4, imagine that the same rounds are repeated. So round 4, we are getting a data 0110. Suppose this is the data. So as per the rule, what will happen? These 2 bits will be appended. So the next data will be 0011 and this will be 1001. So you can observe that these 2 bits have been appended over here, left shifted. Similarly for this part, it has been appended over here. My point is that this segment that we are discussing over here, this is to make the 56-bit key to be even more randomized. That's why I gave you this block over here. I gave you this block randomizing over here. So we got the 64-bit. We discarded 8th bit from each block. So we got the 56-bit. Now we are making the 56-bit divided into 28 and 28. We are calling that as CI and DI for that matter, general term. Now the C and the D will again undergo a randomization based on the rule that which round we are in. If it is 1 to 916, there will be single bit change for the left shift. And the rest of the rounds, it will be 2 bit shifted. So to take that in an example, I'm just taking 8 bit over here. Imagine that there will be 64 such bits. 444 like that. So the same thing will happen. We'll take an example also today and we'll find out that what will be the output. Right? So this will be the randomized key generated after the element is done. But now if you go back to the block, as I mentioned over here, there is something called as PC2. Now this PC2 also has a rule and also sometimes it is formed of a table also, but let us take the rule for the time being. Table we will show you in the PPT itself. The rule is that for C part, okay, CI in general part, discard, please make a note, discard, this is one of the rule actually, 8th, 9th, 22nd and 25th bit. After the randomization has been done, 8th, 9th, 22 and 25th bit should be discarded. Whereas for the D, that is the right hand part, discard 25, 38, 43 and 54th position bit. Now there is no, if you ask me why is there only this specific bit, there is no logic to it. But as per the DES algorithm, these are the standard bits which you need to discard. So you can see from 56 bit, we are discarding basically 8 bit to make it 48. Now this rule that I'm talking about over here, the C and the D, this is just one of the rule. There can be a table which can also signify the same. Suppose the table is only accommodating 48 bits. So basically we have to use a compression table. That also will work. But this is also one of the rules that you are doing. I'll show you in PPT itself that there will be a table also. We can express this in the table format. Same thing, in the table, the random data will be there, except that 8, 9, 22, 25, those will be discarded. Same thing. Okay, that's the logic. So basically we are generating, after all this, we are generating a 48-bit data. And the key now will be of 48 bits. So that's all what we have discussed over here. So if you go back to the PPT, so this 48 bit is generated by all those steps that I told you. So basically we can say it is a 64 bit over here, which goes through a PC1. Okay. After that, it goes to a division where it is becoming C and D. I'm writing in general. Then it goes to some kind of an operation where there is a shifting taking place or a rearrangement is taking place. I'm talking this as a R or the randomized block. And after this is done, we are making the discarding or PC2. And finally, we are getting the 48 bits. So all these steps, the right hand side, whatever I've drawn, this won't be mentioned in your books mostly, but this is how it works. Okay. So the 64 bit goes back to all this process for each and every round I'm talking about. Every round, because each and every time you can see this K1 will be random. This whole process, PC1, C0, D0, PC2 and all this process will be random. Like every round it will work. So for the first round, suppose it will be C1, D1. For the second round, it will be C2, D2. Like that, up to C15, D15. But again, the rules are the same. And the process that I told you that for 1, 2, 9 and 16, there will be single bit rotation. If there is other round, there will be 2-bit rotation. Am I clear with this? From huh. That's what that is a rule. Like it's not that like the C0 part will have 28 bits, right? Because it's a 56. So out of those 28, those bits should be discarded. No, yeah, correct. 35, it should be 35. I wrote it that way. Please change it to 35. I think I mistook it as 25. 35, 38, 43 and 54. Okay, just change it a little bit. In that discarding bit of the last, the PC2. Okay, I think I mistook it to 25. I've written it 25. It should be 35. 25 can't be a part of D. That's correct. So that's why it will be 35. I mistook it. So that's the process of key generation. Now we know about the PC. Left part remains as it is. R is coming in. So this is where we stand at this point. So we now know 32-bit conversion. We now know how this 48 bits generated. We now know about this S box. Okay. And we now know that there might be some permutation table over here. And finally, we are getting this 32 bits over here. This 32 bit again will get XORed with the left hand side of the 32 bit. And that's why we will get a plain text of 64 bit once again. Right? So let's see. Let's move ahead a little bit. So this is S box. I think we can skip a bit. This is not required. This is not required. We are already discussed. So let me just directly go to the diagram or the cipher and the reverse cipher. Basically, this is nothing already we have discussed that whatever we are doing in the transmitter, we are going to do the same in the receiver for a DS, except there is a small change. And let's see the change if you can observe it in the diagram. Can you remember this diagram? I have shown you this before itself. When I was starting with DS, I was telling you that these are all the rounds and this all are my fiestal part. Now what happens ideally, if you look closely to the 16th round, I focused it on a green color over here. If you look at closely, the cipher and the non-decipher process includes that at the 16th round, only the last round, you will find that this happens even in AES as well. This part of swapping is missing. So please make a note of it that for the DES, cipher and reverse cipher operations, other than that, the data that you have made to swap will not be retrieved back. Just the information over here. So the 16th block is different to that of the other blocks. If you observe carefully, there is no such swapping block with like this. At initial stage, when I showed you this diagram, since we have not touched upon this point, I didn't mention that. Now, since we are at the end of DS, remember the last round, the 16th round, there won't be any swapping. Alright, this is just a design strategy, you can say. You can see over there. Using mixture and swapper, we can create the cipher and the reverse cipher, each having 16 rounds. It's just a design criteria, nothing else. Alright. We can, two swappers cancel the effect of each other also. You can see the alternative approach. We don't need that much, but the information is only that. Suppose you are drawing a block diagram or something like that, please remember that the last round will not have a swapper. Suppose I give you the example that this is the data we are getting at the 15th round. what will be the final outcome at the data at the 16th round. So at that time, suppose you remember that each round will have a swapper and you go for a swapping at the end, it will be wrong. Whatever the data you are getting, you can check here, it is a straight connection. There is no swapping that is taking place. So please be very careful while doing it. If the question comes in that what is the outcome after the 16th round, given the 15th round input is this. For the 16th round, there is no swapping operation. Okay? So that's all about the process. This already we have discussed already, so I don't think we need to waste time over here. You can see this is the process which explains the one that I've given you as a class note, where how the 64-bit is converted to 48-bit is being explained. Okay? And if you observe, this 816, this is I already had discussed, so I think we can skip this slide. Also, alternatively, this table can be provided to you, where the same thing will happen, that some of the bits will be removed, meaning the same. Alright, so that's one of the options you can say. If you observe carefully in this table itself, there is no option of 8. Can you see 8 anywhere in the table? Can you see 8th bit or 8 anywhere? No. Can you see 16 anywhere? No. So basically, either you remember in this way, 8, 16, 24th bit will be discarded, or you will be given a table where you can't find 8, 16, 24th bit and all. So meaning the same. Meaning is the same. Okay? So that's already we have discussed. And this is basically the whole diagram of it, which I was drawing a few while back. So you can see these are the 28 bits. Now this goes to a compression box. Alright, so this is my parity drop. We call it the parity drop. Please make a note of this term. Parity drop is the technical term for dropping that 8, 16, 24, 32 bit. That last bit that we are dropping, we call that as a parity drop. This actually is something like PC1, which I have been writing. In different book, it has a different terminology. So parity drop, you can please make a note of it. Alright. Similarly, you can see over here, after a certain period, there is a compression box here. This is ideally the PC2, which I had discussed. For this compression box, either a table will be provided or the logic of that 4 bits, 8, 9, 22, 25 for the left part, and 35, 38, 43 and 54 for the right part will be discarded. Same thing. You can see the table here. This is a kind of given in the textbook. Okay, but maybe from textbook, if you are reading, it might be difficult. You can see the round over here and the number of bits needs to be converted. That's the logic I told you right a while back. So you can observe that for the first round, for the 9th round, for the 2nd round and for the 16th round, there is only 1 bit change. The rest are all 2 bit change. 2 bit shifted, left shift. The same thing I told you, but this is a table format, nothing else. Okay? Alright, so this is again, as I was telling you, that it might be given as a table. This is the PC2, which I told you just a while back. The same thing is given in a table. Are we familiar with this? Is it fine for all of you? What I'm talking about? This is nothing but the PC2 table. What is PC2? I just now had told you the left hand side there will be a discarding of some bit at the end, and the right hand side also will have certain 4 bits which will be discarded. The same thing, if it is not provided, a table will be provided. Based on that, we have to rearrange. Simple as that. Okay? These are the S boxes. Okay. Now let's see the numericals I was talking about. So let's see the first one of the day. And the question is, you have a table given over here, S1 for S box 1, S box 2 and S box 3. So this is my S box 2 and this is my S box 3. The question is, if for each of the table, the data which is being passed through is all 0, then find the pattern, if at all any, and find me the output. Can you please quickly do it and tell me the answer? Very simple. Please do it. You are given this 3 table. One is for S box 1, second one is for S box 2, and the third one is for S box 3. Each of them vary accordingly. You have the same data, all zeros, that is this given over here, given as the feedback to the input. So what will be the corresponding output for S1, S2 and S3? Can you quickly change it to binary, to decimal and all those conversions so that you are in a right space to do the next problem actually? Can you please quickly do it? Remember the rule, the outermost bit will be the row, the middle element will be the column. It's very simple, please do it. It will take 2 minutes to do it. What is your row number over here? I need a few more answers. I guess we have spent enough time to at least answer more than 1 or 2 answers. 0, 0. So your element for the row is 0, 0. So basically if I consider S box 1, so you are looking at somewhere over here. What are the middle element? They are also 0, 0. So basically if you convert back them, so it will be coming as 0 itself. So you are right over here. But suppose instead of 0, 0, there are different values given. So you have to convert that accordingly to the respective decimal values. Take the necessary intersection wherever the value you are getting, convert that back to binary once again. I know even if I tell you, there might be issues with you of conversion. So please go through that, how to convert from data from decimal to binary and all those processes. So in this case, we are getting 14 as the output for the first box. Convert 14 to corresponding binary number, and whatever the data you are getting, that will be the output. Same goes for the other two. Can you quickly do that? At least the conversion to understand, let us understand whether you are understanding it. What will be the first output? Sorry? 1110. Next one? 4 ones. This one? Sorry? 1010. And the reason is the same. Okay, so the decimal number corresponding to it. Since it's a 0, 0, the process is simpler, the calculation is simpler. But if it is given some other data, please make sure you properly calculate and change it to the respective decimal numbers and then do it. Alright? Because based on this, we have the second question, which I think will take a little bit of time. So it is question is, show the result of the following hexadecimal data given as there after passing it through the initial permutation box. So the initial permutation box is provided to you. Look at it carefully. The question is, what will happen about the data after it passes through this box? Can anyone please let me know that how to approach this question, because this is how the questions will come. And this is where it will take time. And unfortunately, at some point of time, you might miss out some bits somewhere and the overall answer will come as wrong. So please be very careful. The questions are very simple, but the calculation, you need a little bit of patience of doing it. How many, this data that you are looking at, this is all in hexadecimal numbers. That's the standard that is being provided to us. So how to approach? First, what you have to do? First, converting to binary, correct? So first, you convert each and every character that you have in store to the respective binary numbers and make the whole data available. So please, can you do that for me? 0110, convert that. I'll give you 2 minutes to please do it, because this practice should be there. Ajay, tell me one thing, in all this scientific calculator, do we have this option? Very good, nice. Then it becomes easier. Then I can add on things. Please do it otherwise, anyway. Tell me first, after you have done it, after you've done the conversion, what is the nature of the data you are getting? That's the binary number I'm talking about. So it will come something like, just like this, you have to go on. This is for 0110, the first 4 that you're looking at. Similarly, for 1023, you will have certain arrangement. So 1023 should come something like like this. It will go on. Now tell me one thing, you don't need to do all the steps. Suppose you have this and it will go on for the rest of the portion of 4110 and 1023, because 1023 is repeated twice, so it will be the same. Now tell me what will be the final outcome. That's most important. Can you read the table and try to alter the data? So 58-bit we don't have right now, and that is the problem. So we have to do that somehow. So let me just write it down. Otherwise, we cannot solve it directly. So let me write it down. 0, 1, 0, 0. This is for the 4110. And the last but not the least, again. So this will be the whole complete set. Right? So this is the whole complete set. Now you have to follow the table in changing the or swapping the permutation, how it is being done. For that, I think it is easier. What I felt when I was doing it, it's easier to mark at least some of the data bits. For example, I marked this one as 8th, this as 16th, this may be as 24th or something like that, or like that, so on and so forth. So that at least you have a reference of bits. So can you tell me the first one, what will be the output or first bit that, what is the first part of the 4 data? What is my 58th bit? 64th is this one. So 60, it should be 0. How come it is 0? Oh, first bit I'm talking, yes. It should be 0, yes, correct. Next bit? Next bit is 50. What is my 50th bit? What is my 58th bit? Is 0. Are we following this carefully? What we have done is, we are arranging this whole data into the pattern form. Now this is my like 1, 2, 3, 4 bit, 8 bit, 12 bit, 16 bit, like that it will go on. So you keep those as a reference. So this is my 64th bit. The last one is my 64th bit. So you can say that this is my 68th bit maybe. Similarly, this is my 56th bit. Okay? Understood? So that's how we are trying to find out. So the first letter or the first conversion after it takes place, 58, 50, 42 and 34. Can anyone give me the complete answer for this? 0, 0, then what is 42nd? 0. And 34th bit? 1. Understood? Similarly, you will go on, like the next 4 will come as 0, 0, 0. 26 bit, 18 bit, 10 and 2. What we are trying to do, this is my reference bit, these are my reference bit, this is my reference table. So whichever bit, 26 bit, we have to find what is the 26 bit over here. Like easy, very easy, 4, 8, 12, 16, 20, 24, 25, 26. So this is my 0. So that's why we are writing for 26 as bit. Similarly, 18 bit. So this is my 16, 8, 16. So this is 0. Got it? So that's how we are rearranging it. But after doing this, we have to convert back this to the decimal numbers, or rather, we have to convert that to hexadecimal numbers, sorry. So we are doing this as 1. This will be like 0. So if I give you the final answer, let me just rub this thing off. Please make a note of it and finish the portion of it. This will be the final answer. Please make a note and try to finish this thing off. For people who are still in a position to not to able to read the table to that of the data, please go back to the previous lectures, and in that I have explained you how to read this table. It's very important. So first we are converting the hexadecimal to binary. Then that is my reference data, reference input. The permutation table is with us. For each data, take the particular corresponding input and then change it. Right? Let me squeeze in another question over here. Please make a note of the final answer. 1066 0099 0088 0088. So that will be the answer. Now, let's see this if you can understand and do it in the same manner. If time permits, we'll finish it. Otherwise, I'll give you this as a task to finish it off. Question is, suppose the key is provided as this. The key is generated like this as a hexadecimal number. Question is, after passing through the data parity drop and subsequently undergoing the permutation table as this, what should be the generated key? Can you understand what the process should be? Can anyone tell me what will be the process of doing this? First process will be, please understand this, very simple. The first process is you have to convert back to binary once again. We are not dealing with hexadecimal number. We have to convert this to, first of all, the binary numbers. Now, so the binary number that you are getting over there, the first part that you have to do is parity drop. So what we are supposed to do in that? 8, 16, 24, 32nd, 48, 44, 48, 56 and the 64 bit should be dropped. The same process you have to apply over here. And after that, whatever you are receiving, the 56 bit of data that you are receiving, that goes to this table. Can you understand what you have to do? So for that, you can see that the table that you are looking at, for that, for each and every bit, you have to change it accordingly. The same way, just like in the previous example we did it. Any doubt here? Any doubt over here? Anyone? The final answer will be of this nature. Again, I urge you to please make a note of the answer. If time permits, or rather, it will definitely be there in the course page, but I want you to please do it back home so that at least you have an idea of doing it. Because this conversion and the reading of the table is very important for solving all these questions. So please make a note of the final answer and you can try out. What you have to do, you have to first convert this to binary. That's the first part. Discard all the 8 bit, 16 bit, 24 bit like that. Whatever you are receiving, that is my C0 and D0. Now, based on that, you go through this permutation table and change it accordingly. Here, although we are mentioning this, but ideally it should have the randomizer block also included. Remember the randomizing block, which round we are in. But for the time being, since we are not considered any round over here, we can eliminate for that, for the timing from our discussion. Ideally, if it is in a round, then after doing the discarding of bits, we have to convert, we have to left shift either 1 bit or 2 bit. Nothing, I am just saying that first of all, you have to convert this whole key into binary form. That's the first part. Now, so after that doing it, the first part of the question indicates you have to do a parity bit drop. So basically you have to remove the 8, the 16, the 24, the 32nd and up to 64th bit. All the last bit you have to discard. So you are getting the 56 bit. So now you have C0 which is 28 bit and D0 which is of 28 bit also. Right? Now the question is subsequently it undergoes the permutation. So for the whole table that you are looking at, convert back based on the input and output relationship, that what will be the final outcome. What I said is that in the theory when we discussed, after this there will be a randomizer block. Based on the certain round, there will be a shifting of 1 bit or 2 bit. But since in the question nothing is mentioned, we don't need to bother with that. But for example, if I change the question over here, that you have the permuted key as this, now find the round 1 and round 2 keys. So what you have to do is, you have to divide first of all the 28 bits from here. So 28 bits means 1, 2, 3, 4, 5, 6, 7. So up to this is C0 and the rest is my D0. C0 and D0. Now, when we are in round 1, we only have 1 bit shift. So, what will happen? For example, 1, 1, 1, 1, 0, 3, 0, 0. I'm just showing the C1 part. 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1. So, this is my C1. Now, if it is in round 1, then there will be one left shift. So what will happen? This one will be shifted over here. So your final outcome would be 1110 0001, because this one will shift it over here. Then again 1001 and so on and so forth. Finally, we'll have a 51 at the end. What I'm asking is, this is my C0 part. This is my T0 part. As per the round 1, there will be one left shift, one bit left shift for C0 and D0. So my left shift, the left bit is 1. So this one should go and add up over here. That's what I've shown. So there will be 1, 2, 3, 4, 5 here. I've just written it down as this to understand, to count the number of bit easy. 4 bit, 4 bit. So this will be 1 over here. Same way the T0 T, what is the left bit? 0. So this will come over here and we fix it. But if it is round 2 and you are getting the same T, what will happen? 1, 1 goes here and connected over here. Round kind of questions you are going to get expect from the questions accordingly. I'll upload a few more of this nature which is given in your textbook as well. Please go through them. The whole detailed steps for finding out this will be there in the course page, which is beyond the time of the class hours. So please go through them. If you find anywhere stuck, please let me know so that I can explain you separately. Alright. So this is all about the DES as the different examples. See, these are the steps I have mentioned. So it's immaterial if I do it over here. You can just go through the course page. I think it will be sufficient to understand. All these things have been told you by some means or the other. Right? So that's where we end our analysis for DES. So next day's class, when we come back, we will finish off with DES, the analysis, the cryptanalysis, why we don't offer DES as often. Why do I need AES for that matter? So that will be discussed, and we will start with the AES part as well. Okay? Thank you.